Bismillahirrahmanirrahim. This is part 3 of the series of videos we are making under the topic of supercomputer on every desk, uh, or HPC on every desk, HPC in virtualized environment, any name you want to give it. This is part 3 and I'm covering MPI, configuration, installation and execution of sample programs in it. So in the previous part I just covered how to configure this MPI, but once again I'll just show it to you that I downloaded MPI from this mcs.anl.gov research project MPI ch2, downloaded 1.0.8 and uncompressed it under an ordinary user's shared home directory. Under this directory MPI ch2 under /cluster is the NFS shared directory on all nodes, and MPI user is my ordinary user. I have already run configure part. This is /configure prefix cluster MPI ch2. This directory will be created once I issue the make command. So I'll do this configure again for you. It will take 2-3 minutes on this virtual machine. So I'll just pause video here. Okay, this is done now. The configure part is done. This part is done. So I'll just do make, which will again take some time, 2-3 minutes. This will actually compile all the options which were detected during the configure phase. I'll just pause it again here. Okay, make part is also complete, and now I'm going to do make install, which will install. Simply place these files in /cluster /MPI ch2 directory. Okay, it should be quick. Okay, done. Right, next I'm going to set up some environment variables in MPI user's bash profile. I will edit. First I'll go to home directory of MPI user, edit .bash_profile, and I'm going to add 2 lines here. Basically I'm going to reduce this line. Okay, this basically tells this operating system that /cluster /MPI ch2 /bin is also part of the path, and LD library path also includes this path MPI ch2 /lib. That is all. And export path and export LD_library path. Fine. Exit that. You may want to source .bash profile if you don't want to log out. So that will load the new values, and you can verify by doing an echo $path. You see this added at the end of the user path directory. Fine. Next I'm going to see if it is able to find MPD. Yes. MPI execute. Yes. And MPI run. Yes, it's able to find all 3 executables. So what I'm going to do now is create an MPD host file. I've copied this commands from my script file I have here. What this does is basically it creates a cluster MPI user mpd.host file, and it puts in that 3 names, master node, node 1 and node 2 in it. We can just check that. Cat this file. Okay, so this has these 3 nodes. Now there's a small mistake in this. I don't want master node to take part in computations. So what I'll do is I'll just edit this file and cluster MPI user MPD host file. I'm going to remove this from the list of nodes. This is going to be MPD Ring. This MPD.host is basically MPD Ring executable. It is going to be removed from future MPI distributions, but anyway we are going to use it for now. Okay, I need to create a secrets file which is slash cluster MPI user dot mpd dot conf. There's a difference between the above file, which is without a dot in the beginning, and it is dot hosts, whereas this file is dot conf. So create this file and specify secret word is equal to red hat, let's say. Fine, exit, save and exit. So once again just check that secret word is equal to red hat. Okay, great. Next I'm going to boot the MPD on the compute nodes, and I'm going to MPD boot MPD. I'll just run MPD. Oh, it says is accessible by others, so MPD has exited. Okay, we need to tighten the permission of this file. Okay, let's check if MPD is running already. It should not be. It's not running. So again MPD ampersand. Okay, now MPD trace will tell you which all nodes. It should trace minus list. It's only showing one node only. That's not right. It should boot on all on two nodes. Okay, so we'll do MPD all exit, and we'll tell it to boot on MPD boot on other nodes. Did boot minus number of machines 2 and minus checkup only. It will tell you checking node 1. There are 2 hosts up. Alright, to keep things simple, what I'm going to do is I'm going to set up MPD to run on all nodes by editing this file. I'm going to say master node is also one of them, or maybe I can just add it at the end, master node. Okay, so once I say that MPD boot on N3, that means all 3 nodes. Okay, great, 3 nodes are up, and now I can, this was checkup only mode, so this time I'm going to boot it on 3 nodes like this, and if I do MPD trace I should get 3 nodes. Great. If I do MPD all exit, I should not get a trace. Great. And if just for a second, if I try to delete this and I say MPD boot minus N2, what would it do? And if I do MPD trace, oh, it does not honor that file properly. Okay, I'll deal with that later. Let's do master node here, and let's MPD all exit and boot on 3 nodes. Okay, and let's do a trace. Okay, fine. So we are good to go. There's a pre-compile. Now it's a time to run the program. MPD is running. MPI can use MPD daemon. So it's, you should know that they are programs provided with the source code of MPI. So let's go one step ahead, up, and go to MPI ch2 directory and go to examples directory. Here we have this file scpi, which is calculate pi, basically the value of pi. It's already compiled. You can see it's already compiled and is executable. So we just need to run that mpi execute minus 2 nodes and 3 nodes. Let's do it on one node first to show you. Dot slash cpi, press enter, and it calculated it in like 345 seconds, milliseconds I should say, or 345 time units. Okay, if I run it on 2 nodes on a real hardware cluster, this time here should reduce, but since it's a virtual cluster, the CPU will instantly get divided into half, and the time will in fact be more. See, the time has increased. If I do it on 3 nodes, the CPU will be divided into 3 nodes because it's virtual, and I'll get this calculation done in more time instead of getting done in 1/3 of the time. But this is, remember, this I started these videos to show you how it's done. On a real hardware cluster, you will see the performance boost instead of getting the performance decrease, but the procedure is same, which I'm doing now. Okay, now I'll also show you how to compile a program. There's a program here, interactive CPI, this one. So how to compile this? This will not get compiled by GCC. No, it will be compiled by MPICC minus output file ICPI and get the file ICPIC. Very simple. That means read this source file and create this output file. Press enter, it will be compiled. It's done. Check ls, and now we have a compiled version of pi interactive calculate pi. Okay, let's run that. mpi execute minus 1 node and dot slash icpi. Let me give it a value 100, 10, 100, 1,000, something like that, big number of intervals, just to give it some time. So it calculated this in like 341 seconds. I press exit and I execute this on 2 nodes now. I give it the same value. Theoretically, in real world hardware cluster, you would see reduced number of seconds, but since this is a virtual cluster, I'm repeating again and again, you will get more wall time here. But surprisingly, this has calculated this in lesser time. This was, is it less time or more time? 1 2 3 4 5 6 time units. 1 2 3 4 5 6. Oh, it has magically some done this in lesser amount of time. Okay, good. This is what actual performance you will get out of a real hardware cluster. For some reason it just worked here. Okay, let's do this on, let's increase the number. Let's increase the number to, a bigger number, which I tested earlier. I will just add 1 0 and let's see how much time it takes to calculate this one on 2 nodes. 1 second. Great. And if I give it one more 0, it will calculate it in 20 seconds. Okay, 17 seconds. It's done it in 17 seconds. Fine. Now let's exit this and let's run this on 1 node. Okay, one node. So now you should see the CPU taking more time because it's not divided across two nodes. I'm talking hardware wise. So let's enter that, and let's enter the last number of intervals I gave, which gave us 17 seconds. If I provide this now to one node only, it will take more time. It should take more time.